Today I'll be finding an easier method to derive the rotational inertia of a cube where the axis of rotation is going straight to the center like so. And before I get into that, I need to discuss a concept. So concept is that we can break the total, we can split the total rotational inertia into its x and y components. And let me show you that. So, I total equals the sum of mr squared, right? So let's just write x and y here. And let's suppose this is a three-dimensional graph. And the z-axis is pointing straight at us. So this z-axis is going straight at us. Can't see it because it's going straight at us. And let's make the z-axis also the axis of rotation. So it would rotate something like this if the z-axis is the axis of rotation. And let's say a point is randomly here. Then what's its r? Well, its r is going to be this length right here, right? And this would be y, and this would be x. Hence, x squared plus y squared would equal r squared by Pythagorean theorem. So hence, we get that it would equal the sum of mx squared plus y squared. Alright? And hence, well, I'm oversimplifying here, but I think you should get the general gist of it. The total it would equal the sum of mx squared and my squared. Hence, the total rotational inertia would be ix plus iy. Now, let's apply it to the present case. So what we're gonna do is we're gonna take a bird's eye view of this cube. We're gonna look at it from above. And before we start, let's make one of the side lengths of the cube s. So that's all of the side lengths, all right? So side length x, and we're gonna take a bird's eye view. That means we're gonna draw x and y again, and let's make this the z-axis. And it's not only is it the z-axis, but it's also the axis of rotation. So now the axis of rotation is pointing straight at us. Remember, we're taking a bird's eye view of this cube here. So z-axis is pointing straight at us. So let's split it up into its x component. So let's try to find ix here. And to do that, we have to take an integral. So to do that, we're gonna split this cube here into multiple rectangles to take an integral. All right. Let me draw a diagram of the rectangles we're splitting it up to. So it's gonna have an infinitely small dx value. So have an infinitely small, or I think this is the width, right? Or it doesn't matter. And these two sides would be s. So the volume of these infinitely small rectangles would have a volume of s squared dx. So let's write that there. Oh, and we're going to take an integral from, well, this point is negative s over 2, and that point here is s over 2. So we're going to have to take well, let me just write it down here. An integral from negative s over 2 to s over 2, and the volume, as we said, is s squared dx, right? And yeah, that's the volume. Now we need to know the density. Well, the density is just total mass over total volume, and the volume of a cube is just one of its sides cubed. So if we multiply density here, and now we get mass, finally we need to add like a further x squared here, because we're trying to find the sum of mx squared. So this gives us the mass, and this gives us the x squared. So we take an integral of this. So ix would equal, let's take out the constants. dx, all right? And this would obviously be s squared times x cubed 3 from negative s over 2 to s over 2. This just simplifies down to s over 2 cubed over 3 minus negative s over 2 cubed over 3, and this just equals, well, s cubed over 24. The negatives cancel out, s cubed over 24, and hence we get s cubed over 12, all right? So Ix would equal s squared times density times s cubed over 12, and let's change the density into the mass over volume formula. Ix equals s5 over 12 times m over s cubed, and hence we get, well, just ms squared over 12. So that's Ix. Now we need to find Iy. For Iy, well, you'll find that it's remarkably similar to finding Ix. So if this is y, this is x. Then Iy, in the case of Iy, we split it up into multiple rectangles like this, and that would be Iy. And if intuitively, you know that the Ix would actually equal Iy. So then what's Ix plus Iy? So if Ix equal Iy, then that means Ix plus Iy equal 2Ix. And hence, we just double this, and this just equals I total, right? So IT equal 2Ix, which equals double this, ms squared over 6. And then that's the proof. So what I did here was I split the rotational inertia into its two components, x and y. I made the z-axis the axis of rotation. So yeah, that's what I did. And I hope you understood what I did in this video. And oh, and I also learned that there's also, you can't use this, it's not advised to use, or I don't advise you to use this method for everything. So if you're looking at a sphere, right, you shouldn't use this method for a sphere because you get a really hard integral. You should only use this method for rigid objects like a rectangular prism or a cube or maybe a triangle, but never use it for a cone, never use it for anything circular. Only use it for, you know, something with sharp edges like that. You should use this you should use this method for something with sharp edges. All right, thank you.